Okay, this is part 2 of our discussion, chapter 2, electrostatic. So last discussion, we discussed the Coulomb's law, the two basic laws in electrostatic. Then in this part 2, we will be talking about electric field intensity. And before we do that, we first have some examples under Coulomb's law. So this is an example. There are three equal positive charges of 10 stat coulomb. Each are located at the vertices of an equilateral triangle of 2 centimeter length. What is the magnitude of the force acting on each charge? So to solve this one, we actually don't need three-dimensional or vector analysis in three-dimensional in this example because the charges are located in the vertices of an equilateral triangle. So what does this mean? We can just do a two-dimensional XY plane. We can just use XY plane to plot these three charges, and you want to determine the magnitude of the force acting on each charge. So because this is a equilateral triangle, so it's very obvious that the forces on each charge should be the same because they are all equal charges and they have all the same distance from each other. It's 2 centimeter. So let's try to draw a equilateral triangle. Draw. Here, let's assume this is an equilateral triangle. And at the vertices, we have charges that is, or dot are equal to 10 stat coulomb. So let's say this is Q1 here, 10 stat coulomb. This is Q2, which is also equal to 10 stat coulomb, and this is Q3, 10 stat coulomb. Now, the distance between them, the side of the equilateral triangle, when we say equilateral, the sides are all equal, and it's equal to 2 centimeters. So this length here is 2 centimeters. This is also 2 centimeters, and this is also 2 centimeters. And we want to determine the forces acting on each charges. Let's start with the Q1, F1. So what are the forces acting on Q1? Because there are two other charges around this charge Q1. So just like what we discussed last meeting, we can apply superposition theorem. We can remove the other one, then we determine the effect of the other one. So here, if we remove Q3, disregard Q3, then what will be the force? These are all positive charges. Remember the first law. Positive charges repel. So the direction of the force should be opposite direction. It should be the repelling direction. So it should be here. And the effect coming from Q2 should be somewhere here. This force here, let's just call it, because it's from from 2 to 1, so let's just call it F to 1. Then, so that's the effect of Q2 when we apply Coulomb's law. Then, let's do that again now, but now we remove Q2. We look at Q3, and what will be the effect? It's still both positive. So the direction of the force should be in this direction. Then if you want to determine, this is F3, let's call it F31, from 3 to 1. The force on Q1 due to Q3, F31. So now if you want to determine the net force at the Q1, then we just need to add these two vectors here, F21 and F31. So we can use the parallelogram method in adding vectors. And this should be the result. This should be the force acting on Q1, and we will call it F1. So if you look at this one, F31 and F21, the magnitude here should be also the same. Because if we try to solve them, the distance between them is the same, and the charge of Q1 and Q2, Q1 and Q3 is also the same. So if we solve F21 and F31, then it should be the same. Now, let's do this one without using our or we use the basic math, vector analysis. So if we want, so these are vectors. It's obvious from the drawing that the direction of F1 should be in that direction upwards. So if this is in, let's plot this one in XY plane. So if this is the y-axis and this is the x-axis, this is the x-axis, if this is the y-axis, then the direction should be AY, because it's going in that direction. Then this point will be 0, 0. This point here should be 2 and 0. And this one here, what should be the point here? So it's in the middle. This is 2 centimeters, so 1 and 1. So it should be 1. Then what should be this length from here to here? And it's right triangle, so we can use Pythagorean theorem to solve that. It should be equal to the square root of 2 squared minus 1 squared. Or this is 1, the square root of 4 minus 1. Or that's square root of 3. So that should be the coordinates if we plot this one in XY plane. So the direction of F1 obviously should be in AY direction. The direction of F21 is this one. So if we solve for F1, we just need to add the forces in Q1. So what are the forces? We have F21 and we have F31. And we will solve them individually. Although we know that they are equal, but the direction is not the same because we are talking about vectors. So F21 now, solving for F21. The force due to 2 at Q1. So this will be Q1 times Q2 all over. Let's assume this is in air or space. The medium is air. So we can use the K constant here, directly the K constant. K. Then this will be R squared or R cubed, multiply it with that R, and this R should be R21. Let's call it R21. And this will be R21 here, from here to here. Then, what is R21? R21 is obviously from here up to this one. So this should be R21. R1 minus R2. So this R1 here, the position vector from here, and the position vector from here. And that should be 2 so this should be R21. R1 minus R2. Our R1 will be this one. Let's draw another color. From here to here, this is R1. Then from here to here, this is R2, or this is R2. This is R1 because it's R2, R2, 1. No, R2, 1. So this should be R2. And this is R1. R2, 1. So R1 minus R2. What will be R1? That's 1 square root of 3. And what should be R2? This is R1. And this is R2. R2 is, because this is Y is 0. So it should just equal to 2AX. R1 is AX. Then you have plus square root of 3AY. So So now I can just write this one in another way of writing a vector, position vector. It's just like a coordinate. And this is 1 square root of 3, 0. Then you subtract R2, 2, 0, 0. So R21 now is we just need to subtract that. R21 will be equal to 1 minus 2. Then we have square root of 3 minus 0. Then 0 minus 0. So this is negative 1 minus 2 is negative 1 in the x direction. Then we have in the y direction square root of 3 minus 0, or that's positive square root of 3 ay. So that is our R21. And the magnitude of R21 is simply equal to 2 centimeter. So if we know that it's 2, but if we try to solve using that vector that we derive, this should be the formula 1 squared plus square root of 3 squared. So this will be square root of 3 squared is 3 plus 1 is 4. Square root of 4 is just 2. So basically, the 2 centimeter here is correct. Also, even if you don't know that, you still use this one. Then you can now solve for F21. F21. So what should be the value of K here? Our value for K should be equal to 1 because we are in CGS system. Our charge is in Coulomb. Our distance is in centimeter. So we can use the CGS system. So K here is equal to 1. Then Q1 times Q2, it's the same 10 Coulomb, 10 Coulomb. We just square that 10 times 10. All over the distance between them, 2. Then we cube that. Then you multiply it with the vector R21. Negative AX plus the square root of 3 AY. Now, if you are only interested in the magnitude of the force, you can also do, instead of using this formula, we can make it F21 equals KQ1, Q2 all over that R squared. Then you multiply it with AR, or AR is the direction. And that direction, you just remove that one, then you get the magnitude. So whatever this value here, then that will be the magnitude. You can also do that. Or you can still use this one, but later on, if you want to determine the magnitude of F21, you take the square root. So let's try that. F21 equals 1 times 10 squared over 2 squared. Then what is the unit vector? It should be negative AX plus square root of 3 AY. This is R21. And you divide it with the magnitude, which is 2. And this is now the unit vector AR21. And this means that this is the direction and this is the magnitude. So if we want to determine the magnitude, before we do that, F21, 10 squared over 2 squared. So 10 divided by 2 is 5. 5 squared is 25. So this is 25. Then you multiply it with negative 1 half ax plus the square root of 3 over 2 ay. And I don't need to distribute this now because I'm only interested to the magnitude, because this is the magnitude and this is the direction. So to solve for the magnitude, but before that, we need the direction, because what we want is the magnitude of F1, not the magnitude of F21. So that's still correct. Then next, we solve for F31. So it's the same way as what we did. So this should be 10 squared over 2 squared. Then this time, here will be R31 divided by 2. Or what is 2? It's still the magnitude of R31. What is R31? Where is R31? R31 is this one. R321. And that is actually equal to R1. R31 is actually equal to R1. So what is our R1? Our R1 is 1 square root of 30. And we can use that one here. So this will be F31 now will be equal to 10 squared over 2 squared, 25, with the direction of negative 1 half, or correct, 1 square root of 3. It's positive 1 half. Instead of negative, it's positive 1 half. AX, then plus square root of 3 over 2 AY, where R31 is equal to AX plus square root of 3 AY. Where does this came from? It's the same as R1, which is this one, 130 here. This is AX and this is AY. So that is now our F31. So if you want to solve for F1, we add them. So F1 will be equal to F21 plus F31. So we can factor out that 25. Then we add AX and AX, so negative 1 half plus 1 half. So that should be equal to 0. Then square root of 3 halves plus square root of 3 halves. So just multiply it by 2. Or you multiply it with square root of 3 AY. Then you multiply 25 to square root of 3. 25 times square root of 3 will be equal to 43.3. So F1 will be equal to 43.3 in the y direction. So just like what we predict from the drawing, that the direction of F1 will be in the y direction upward. It's positive direction of y. And we also came up with the same solution. The direction is also EY. And the unit here is not Newton, it should be in dynes. That's the force on F1. Then at F2, at Q2, what should be the force at Q2? It's still the same magnitude, but obviously the direction should be in this direction. You can just write the direction. That this is F due to 3, F3, 2, and this is due to 1, F1, 2. Here we have this is due to F1, 3, and this is due to F 2, 2, 3. Then for the net forces, it should be this one. This will be F 2, and also here this should be F3, F2 and F3. And the directions are we have y and we have x. So it's not just ax, it's not just ay. Should be, if I get this one, it should be this angle here is 60 degrees. So this is also 60 here. So if you divide that, 30 and 30 degrees. 30 degrees. So we can convert this one into polar form. F2 is 43.3 with the angle of negative 30 degrees. Here, the angle will be, instead of negative 30 degrees, this should be 180 plus 30. And that is 210 degrees, or negative 90 plus 30. 120, negative 120 degrees. F3. And they're all 25 or 43.3 lines. So the magnitude now at F1 is 43.3, which is also the same as the magnitude in F2 and also the magnitude in F3. They have all the same magnitudes. Why? Because they have all the same charges and the same distance. The only difference between them is their direction. Okay? You can practice to solve F2 and F3 using this process here. And there is an easy way to use this one using the complex analysis from circuits 2. You put angles here. This is just like a vector diagram in circuits. You can do that. You just use complex. And it's easier if to use that in this kind and type of problem. But you need to practice this process here. This is a longer solution. I admit this is a longer solution, but this solution is the solution that we need so that we can continue later on for the harder examples in three-dimensional. You need to familiarize yourself with this type of solutions, not the shortcut. The shortcut is you just use F1 is equal to, here you have 25, F21 is 25, and the angle here, because that is 60 degrees, the angle here is 180 minus 60, and that is 90 plus 30, 120 degrees. So F21 is 25 angle 120 degrees. Then you add that with F31. Well, F31, this angle here is 60 degrees. So this is also 60 degrees. So F31 is 25 angle 60. 25 angle 60. Then if you use your calculator to solve this, it's obvious that the angle should be a 90 degrees angle because it's going upward. So if you try to solve this using the calculator in complex mode, shape mode, complex, then so we have 25 angle 120, then you add it with 25 shape angle 60 degrees, and equals, this is in rectangular, we need to convert this one into polar form. Wait, the mode it should be in degree mode, not in region mode, because I use 120 degrees and 60 degrees. Now, if you look at this one, so shift, so it's 43.3 something. I means in the y direction, or that's equal to 90 degrees upward. So you can do that, and you will also come up with a 43. If you just want the magnitude, 43.3 dynes. Okay, now let's take another one, another example. 2-point charges 10 centimeter apart exert a force of 1 times 10 to the negative 3 grams on each other. If the charges are the same value, what is the value of each charge in stat column? So this one, if we look at this problem, the force is 1 times 10 to the negative 3, and the unit is grams. So we need to convert that one into, because this is in CGS, we need to convert that into dyne. And remember, 1 Newton is equivalent to 1 kilogram meter per second squared. This is mass times the gravity. That's the formula for the force and the mass. F equals m times g. That's the unit. That's why the unit for Newton is kilogram. It's the same as kilogram meter per second squared. And for dyne, 1 dyne, because this is in CGS, it should be equal to 1 instead of kilo. It should be gram CGS. Then instead of meter, it should be centimeter per second squared. So CGS. So 1 dyne is 1 gram times centimeter per second squared. Now the given here is in grams. So what do we do to make it in dyne? We just multiply it with the gravity. So 1 times 10, 1 times 10 to the negative 3, this is in gram. To make it dyne, we need to multiply it with centimeter per second squared. And that is actually the gravity. And the value of gravity should be around 98. We can use 981 centimeters per second squared. So you just multiply this one with 981 centimeter per second squared, so that it will become a dyne. And this is equal to 0.981 dyne. It's now in dyne, the force. And we can now use directly the formula. We don't need to care about the directions here. We just care about the value of the Q. F equals, the magnitude of F is equal to K times Q1 times Q2 times the distance between them. What's the distance between them? The distance between them is 10 centimeter. And we use K equals 1 because this is in CGS. But we want Q1 and Q2 are the same, so this is just K times Q squared over the distance. So if you solve for Q squared will be equal to, and this is equal to 1, F times the distance. And you square root that, Q will be equal to the square root of the force, which is already solved, 0.981. And you multiply it with the distance square. It should be square. 10 centimeter, so multiply it with 10 square. So the unit here, because we are all in CGS, 981 is in dyne, then here is in centimeter. So the unit here should be in stat column. So Q will be equal to 9. Square root of 0.981 times 10 squared. 9.9 stat column. 9.9 stat column. And that is the value of the charges in stat column. Because the problem is asking for the value of charge in stat Coulomb. But if the problem asks in Coulomb, you need to convert this one, and I already gave you the conversion of stat Coulomb. And another problem here, two electrons in a vacuum experience a force of 2 times 10 raised to negative 15 Newton. Now the question is, how far apart are the electrons? If you look at this one, it's just like if you use the formula again, it's the magnitude F is equal to K Q1 times Q2 all over the distance squared. We don't have Q. I don't see Coulomb in the problem. Then how can I solve for the distance if F is given and what else are given? There's no other given, and I want to solve for this one. K is also given, this is equal to 1 because it's in vacuum. Now, how do we solve this one if we don't know the charge? Now, the problem says it's at two electrons. So what does this mean? 2 electrons in a vacuum experience a force. So there are 2 electrons. Remember Q. What is Q? It's the charge. Remember the definition of charge. Charge is just the accumulation of electrons. And actually, we have a conversion for that. So if there are 2 electrons, 1 electron here and 1 electron here, then what should be the distance between them if the force experienced by the 2 is 2 times 10 to the negative 15? But this is not in Coulomb, so we cannot just substitute 1 in the formula. You need to convert that into Q. So Q1 here and Q2 is the same. Q1 is equal to Q2. And this is equal to this. They are all 1 electron. But we need to convert this one into Coulomb. So how do we convert that? 1 Coulomb, inside the 1 Coulomb of charge, how many electrons are there? There are 6.25 times 10 to the 18 electrons in 1 Coulomb. This is in your calculator actually, so you can also use your calculator. You don't need to memorize this one. So the charge now will be equal to 1 divided by 6.25. And that is actually equal to the charge of 1 electron, 1.6 times 10 to the negative 19 Coulomb. So there's now the Coulomb that we want. You square that because we want to solve for the distance. So R squared now, the distance, is equal to Q1 times Q2, or simply 1.6 times 10 to the negative 19. And what we do is we square this one, then we divide it with the force, cross multiply. That's the force. The force is 2 times 10 to the negative 15. 2 times 10 to the negative 15. And look at the units. This is in Coulomb and this is in Newton. So these are in MKS system. Your K here is not equal to 1 because we are in MKS system. So this should not be equal to 1. And what's the value for our K if you are in MKS? If you are in MKS, K is equal to 9 times 10 to the 9. If in CJS, it's equal to 1. But it's not in CJS, it's in MKS. So we use 9 times 10 to the 9. So where is that K now? You still need to multiply this one with K. And that is 9 times 10 to the 9. And that unit will cancel out so that the value for this one should be in meters. So now, you take the square root of that. You multiply, then you take the square root. So the answer will be square 1.6 raised to, wait, 1.6 raised to negative 1.6 raised to negative 19. Then you square this, then you multiply it with 9 times 10 to the 9 times 9 times 10 to the 9. Then you divide it with the force, which is 2 times 10 to the negative 15. 2 times to the negative 15. And equals, then you take the square root of that answer. It should be 3.39 raised to negative 7. So the distance now between that charge or the electrons will be equal to 3.39 times 10 to the negative 7. And the unit here should be in meters because we are in MKS system. So that's it. Last example. We can take another last example. This one. Find the force on a 300,000 stud column charge that is located at 300 in centimeter. If four like charges of 60,000 stud column are located on the x and y axis at plus or minus 400 centimeter. So this is x and y axis. So there are four of them, plus and minus in x and plus and minus in the y. So if you try to draw this one, let's use algebra to plot this one. So this is the plot. So these are the four vectors. And we want to solve the effect or the force at this point. I'll just try to snip that one. Here, so we have now the figure. So here, I want to solve for the force at this point here. And the charge here is actually, let's call it Q1. Or just simply Q, which is equal to 300,000 stat C. Then all the charges, so this is positive, so or all the charges here, let's call it this point, they are all 60,000 stat column, 60,000 stat C, 60,000 stat C, 60,000 stat C, and 60,000 stat C. And again, if we observe, what will happen? What will be the direction of the force at that point? At charge 300,000 stat coulomb. Obviously, because this is symmetrical, again, this is symmetrical. They have all the same charges, and they are all have the same distance from each other. So the net force should be in this direction. I will predict the net force will be in the z direction at that charge F. So now we want to prove and we want to determine the magnitude of that. Not just the magnitude, but also the direction of that force F. So how do we do that? Superposition. We use again superposition, and we consider each of them, and we add them. So what's the effect from the different charges around that 300,000 stat coulomb? Then to do that, let's just call the charges around this one. Let's call this one Q1. Here, this is Q2, and this is Q4, and this is Q3. and this is Q. So the forces due to these Q's, we can just call them F1, F2, F3, and F4. And we call this one the total. F total, the net force, will be equal to the force due to Q1, the force due to Q2, the force due to Q3, and the force due to Q4. And again, we will solve individually F1, F2, F3, F4 using superposition theorem. So first, let us determine the displacement vectors one by one. This will be, so this is Q1, so let's call this one R1, and this will be R2, and this will be R3, and this will be R4. And the position vectors will be in here and in here. So they are all the same. This one is 400 in X, this one is 400 in AY, and this one is negative 400 AX and negative 400 AY. And the upward, the Z component will be always 300 AZ. So for R1, we can solve R1 directly here. R1 will be equal to the end. What's the end point? The end point is this one. And what's the position vector at this point? This should be 300 AZ. Then you just subtract it with the start, and this is 400 AX. So R1 is just equal to 400 AX, then plus 300 AZ. Okay, then R2, and for R2, this is our R2 here. So again, it should be 300 AZ. Oh, wait, this should be minus. Yeah, I forgot, it should be minus because it's going into that direction. It's 0 minus 400. Then 0 minus 0, then 300 minus 0. Here in R2, it should be again 0 minus 0, there's no x component. Then 0 minus the y component is negative 400 AY, then still positive 300 AZ. Then for R3, this should be in that direction, so it's negative the 0 minus negative 400, so it should be positive 400 AX. Then still plus 300 AZ. Then lastly, for R4, the displacement vector R4 will be again 0 minus 0, so there's no x component. Then 0 minus there's a y component, it's negative, so it should be positive 0 minus negative. It's positive 400 AY, then you add 300 AZ. So these are now the position vectors. We need this to determine the F1, F2, and F3. Then after that, the distance, the magnitudes of these 3 or 4 vectors are all the same, and that's the distance r. Let's just call it distance r. They're all the same, and it's equal to the square root of 400 squared plus 300 squared. And that should be equal to 500 centimeters. So that's the magnitude, not centimeter. You can just remove the unit, 500. What do we need? Still need here. It's fine now. So we can now do this one. So F total will be equal to F1 plus F2 plus F3. Now the charges are the same. They're all positive. So the Q1, Q2, Q3, and Q4 are all the same. So we can factor that out. So I can still, I write the formula first. F1, Q1 times Q. So you multiply it with K all over uh, R cube times R1. This is due to F1. Then F2, Q2 times Q all over still the same magnitude. This is R2. Then plus K Q3, then Q all over R cube, then R3, then lastly R4, K Q4, Q over R cube, then you multiply it with R4. You can simplify this one by factoring out the common. What are the common? Q, K, and R cube. So this will be so we factor them out. K, then we have Q over R cube. So these are the common factors. Then we have Q1 times R1 plus Q2. And also we can factor out actually Q1, Q2, Q3, and Q4 because they are all equal. They are all the same. They are all equal to 60,000. So you can just factor them. Just write this one. I just put the values. I can just put the values. What should be the value for K? 9 times 10 to the 9. Or you can use 1 over 4 pi times epsilon naught. You can also do that. Then Q1 is Q1, Q2, 60 stat Coulomb. Wait, this is stat Coulomb. This is in CGS system. It's not 9 times 10 to the 9K. Our K here should be equal to 1. So it's good. It's equal to 1. So we just need to multiply Q and Q. Then we just add all the R1, R2, R3, R4 vectors. So Q1 is 60,000. Then you multiply it with Q, which is 300,000. Then you divide it with the distance, which is 500. Then you take the cube of this. Then next is we just add all R1, R2, R3 plus R4. R1 plus R2 plus R3 plus R4. So we just add all this R1, R2, R3, R4. 400 AX. What are the AX here? 400 plus 400. Or negative 400 plus 400. So AX will cancel out. Then negative 400 AY plus 400 AY. AY will also cancel out. So AX and AY component will all cancel out. It's obvious because what we predict is it's just the Z component. So it's correct that our prediction is that direction. So we just add all the Z components, 300 plus 300 plus 300 plus 300. So 300 times 1, 2, 3, 4 times 4. So that's equal to 1,200 AZ. So this will be 60,000 times 300,000. 60,000 times 300,000. Then you divide it with 500 cube. This will be equal to 144. there should be 144 times this one, which is the AZ, times 1,200 AZ. Then you multiply 144 with 1,200. And this is equal to 172,800. So the force, total net force, AZ, this is in dynes. Now, if you want to solve this, or we want the problem asked in Newton, you can convert that in Newton. What is our conversion? Dynes to Newton. 1 Newton is equivalent to 100,000 dyne. So if you convert that in Newton, so 170,800, this is in dyne. 1 Newton is equivalent to 100,000 dynes. So if we divide it with 100,000, this should be around 1.728 or 1.73 Newton. So in Newton, F will be equal to 1.728 AZ in Newton. So that is Coulomb's law and superposition. So the next topic, we will be starting electric field intensity in the next video. Okay.